Welcome, everyone. Are you ready to unlock what's literally one of the most fundamental superpowers in computer science? Because whether you're building the next massive social media platform, some crazy high-frequency trading bot, or honestly just a simple mobile app, how you organize your data completely dictates your success. In this explainer, we're going to look at the crucial art and science of organizing that data efficiently. We are laying the groundwork for how you should think about memory, speed, and problem-solving in software development.
Okay, let's dive into this. Here's a quick look at our agenda. We're covering 1. An introduction to data structures. 2. Costs, benefits, and goals. 3. The course roadmap. 4. A problem involving massive linear arrays. 5. The solution using a dictionary data structure. And 6. Key takeaways and recap.
Section 1. Introduction to Data Structures.
So think about the computer science pipeline for a second. It shows exactly how our knowledge builds on itself, right? You start your journey with Intro to CS, getting a feel for the raw hardware, basic software, operating systems. Then you step up to computer programming, actually writing code using procedural and object-oriented techniques. But right here in the middle, acting as this totally critical bridge, is data structures. This is where we answer the big question. How do we organize information in memory so we can actually use it efficiently? You absolutely have to master this bridge before you can even think about moving on to the final stage, algorithm analysis, where you mathematically prove the speed and efficiency of your code.
Now, formally speaking, a data structure is a representation used for storing information. It provides a specific way to organize, access, and modify a collection of data items. Honestly, in a general sense, anything used to store info, simple integers, standard structures, classes, arrays, is technically a data structure. But usually when we use the term in computer science, we mean organizing a much larger collection of items. And here's a super important concept to wrap your head around. Data structures don't just sit there like static boxes in a warehouse. They come paired with algorithms to actively perform operations on that data. You always need accompanying algorithms to search for an item, insert a new one, or remove an old one. The structure and the algorithm are basically two sides of the exact same coin.
Section 2. Costs, benefits, and goals.
Okay, we really need to talk about the universal trade-off in computer science, time versus space. Every single data structure requires a certain amount of space, which is just the physical memory needed to store your items in RAM or on disk. But at the exact same time, every structure requires time, meaning the CPU processing effort needed to perform basic operations like inserting or searching. The cost of a data structure is essentially the time and space it eats up. It's a lot like packing for a trip, right? You could perfectly fold and vacuum seal everything to save space, but man, that takes a huge amount of time. Or you could just throw everything loosely into a giant suitcase in 2 seconds, saving time, but taking up way too much space. It's incredibly hard to find one data structure that is perfect for every situation. The best choice always depends on your specific data and how often you run operations. Definitely keep this time versus space trade-off in the back of your mind. It's a golden rule for your exams and, well, for your entire engineering career.
This brings us right to our core goals. By the end of our time together, you're going to learn the most commonly used data structures, basically building up a really versatile programmer's toolkit. We'll rigorously examine the specific costs and benefits of every single one, constantly weighing those time and space trade-offs. And most importantly, we're going to apply this theory by analyzing real-world case studies. Mastering this toolkit is exactly what separates an average coder from an expert software engineer who can build truly scalable applications.
Section 3. The course roadmap.
Let's take a quick look at how the semester breaks down. The curriculum is sharply divided right at the midterm. For the first half, you are responsible for simple and abstract data types, some background on algorithm analysis, and linear structures. So we're talking standard arrays, searching and sorting, linked lists, queues, and stacks. These linear concepts are your baseline. Then, once you crush the midterm, we move into much more complex, non-linear territory. We'll get into tree terminology, binary search trees, AVL trees, B+ trees, and follow that up with advanced stuff like graphs, hashing, and heaps. It is a packed schedule, for sure, but it builds perfectly, step by step, so you have the mathematical logic you need before hitting the really hard algorithms.
Section 4. Problem: massive linear arrays.
Imagine a cellular service company. They have a massive database of 10 million active users. Let that sink in. 10 million. That is an enterprise-level scale. And when you're dealing with 8 figures of data points, it introduces some serious performance and memory challenges that standard out-of-the-box programming techniques just can't handle.
Now, this company issues cellular contracts, but because of some strict new security rules, they absolutely cannot issue multiple contracts to the exact same user. So they have a rigorous method for detecting duplicates. Before issuing a contract, they have to search the user's ID in their existing database. If it fails, meaning the system cannot find the ID, they go ahead and safely issue the new contract. But if it succeeds, meaning that ID is already lurking in the system somewhere, they immediately reject the application to prevent a duplicate.
If we build this verification protocol using a basic linear array, our database is literally just one massive flat list. We have 10 million continuous entries made up of 3 fields: a national identity card, or NIC number, a name, and an address. This could just be a structured array or an array of class objects. A new request comes in, the system starts searching through this huge array and then branches to not issue or issue, depending on whether it hits a match.
But wait, think about this for a second. What is the glaring edge case here? If this database holds 10 million users and a brand new customer applies, the system has to search through millions of entries, one by one, from the very top to the very bottom, just to verify they aren't in there. That's up to 10 million individual operations just for a single contract verification. The massive disadvantage here is the incredibly slow O of n bottleneck of a linear search. In Big O notation, O of n means the time taken scales linearly with the number of users. The time cost here is completely unacceptable. Your users would literally be waiting minutes just to get approved. No way.
Section 5. Solution: Dictionary Data Structure.
Fortunately, we can drastically fix this horrific time cost by using a dictionary data structure. The core idea is to logically group similar records together. In our case, we can use the first digit of the user's NIC number. We basically create a dictionary entry for each distinct digit, 0 through 9. For example, NIC numbers starting with 3, like 3419668-1, are grouped strictly under the dictionary entry for 3. By doing just this one simple thing, you instantly eliminate 90% of the database from your search. You don't have to check millions of records starting with 1, 2, or 4. The search now happens in 2 lightning-fast steps. First, search the dictionary entry to find the right group. Second, search for the specific contract only within that much smaller group.
To see how this grouping works under the hood in memory, imagine the dictionary items acting as a primary index, like 0, 3, and 6. Instead of searching a flat list, these are your entry points. Through memory pointers, they map directly to smaller subarrays holding the actual data. If a new ID starts with a 3, the algorithm instantly jumps to the 3 bucket and only searches the specific chain connected to it. It perfectly skips all the other millions of irrelevant buckets. We achieve this incredibly efficient routing entirely by using pointer mechanics.
Programming these connections means maintaining pointers right alongside our structures, and here is an absolutely crucial syntax rule you'll want to remember for exams. A non-null pointer indicates the presence of a next record. If the pointer has a physical memory address, you just follow it to the next piece of data. But, and here's the magic, if it points to null, you've reached the very end of that specific dictionary group. Once your algorithm hits null, it instantly knows the ID isn't in the system, and it can safely issue the new contract without checking millions of other random records.
Section 6. Key takeaways and recap. Just to wrap things up really quick, remember, data structures don't just hold data, they organize it in memory alongside the algorithms needed to manipulate it. As you write your code, you always have to balance that time versus space trade-off. It's basically the central dilemma of all software engineering. And as we saw with our 10 million user case study, picking the right structure changes everything. By switching from a flat linear array to a grouped dictionary structure using pointers, we turned an unbearable bottleneck into an instant lookup.
I'm going to leave you with this thought. Choosing the right data structure is the ultimate superpower in computer science. Are you ready to build your toolkit? Seriously, think about how you organize data in your own projects. Are you using a massive sledgehammer when you really just need a precise scalpel? Keep that mindset sharp as we move through the semester, and I'll catch you in the next explainer.